Alright, you've done it. You've made it to the very last section of physics. So this is chapter 11 notes, the final section, the final video for physics. So we're going to talk about basically the quantum mechanics, the electromagnetic spectrum. So we're going to basically talk about what this giant picture means. So let's start. Electromagnetic waves. So we've been talking a lot about waves, and so we're going to talk about a specific type of wave called electromagnetic waves. And so I'm going to abbreviate a lot of times and just call them EM waves. Helps if my pen will work. I don't know why it's not showing up. Who knows? Maybe if I do it as a pen. There we go. So EM waves. A lot easier to talk about than saying electromagnetic every time. Okay, so electromagnetic waves. These guys do not need matter to transfer. Okay, so they are not mechanical waves. So no matter necessary. They are made from vibrating electric charges. So electric charges, they start to move, they start to groove, and so because they are moving and grooving, we get these electromagnetic waves. So because they don't need matter though, they're able to travel through space. So we talked about transverse and longitudinal waves, and they need mediums. So they, we can't send them technically into outer space, so here we go. Here's the type of wave that we can send into outer space. So these guys, as we said, they transfer energy between vibrating electric and they move because of the vibrating electric charges. So the energy moves because of these vibrating electric charges. So they have these electric charges. So because they have electric charges, they create magnetic fields, and so they transfer energy between electric charges. So they electric and magnetic fields. Okay, so all matter contains charged particles, so that are always moving. So everything emits electromagnetic waves. So everything that we see, everything that we touch, everything that we are exposed to has an electromagnetic wave. Okay, so right now, as you are looking at this screen, you are being exposed to an electromagnetic wave. Here is what an electromagnetic wave looks like. This is like a Mac Daddy transverse wave. It is a huge transverse wave, because if you look at it, it's really, if you look at the red, look, up, down, up, down, up, down. Same thing with the blue, up, down, up, down. So it's basically like two transverse waves overlapping each other. So that's why I call it the Mac Daddy, the big transverse wave. So that's what a electromagnetic wave looks like. So, and I also think of it as a transverse wave because it has all the properties of a transverse wave. So look here, they even put look, here's the wavelength. So it has a frequency. It has all those things. And so the red they're showing you, here's the electric field. The blue, here's the magnetic field. So it has all those, it has those properties. So properties, as we already talked about, it has a wavelength. It becomes shorter as the temperature of that material goes up. So if it gets hotter, that wavelength shrinks. It carries radiant energy, so like sun energy. Travels. What speed does it travel at? Travels at the speed of 3 times 10 to the 8th meters per second in a vacuum. And remember that a vacuum means that there is no matter, basically space. Okay, and it travels at 3 times 10 to the 8th in space. So if we are traveling at here on Earth where there's air, or if we're trying to put it through water, it's going to be slower. So it depends on what you're traveling through. That number is going to be lower. That's if you're traveling through space, 3 times 10 to the 8th. We call that speed the speed of light. That's what it means. So if you ever look in my room, I have that over by the shower, I have that sign that says speed limit C. That's what that means. We're traveling at the speed of light. C stands for the speed of light. Nothing travels faster than the speed of light. That is the absolute fastest speed that you can ever travel. Okay, now there came a point in time where in the early beginning of science where we have waves and we have particles. Two different things. And by particles they mean like electrons. And so they said that a wave is just this thing that carries energy. It's just this disturbance. Like you drop a pebble into water and you know it makes waves. That you have just this woo woo. Why my pen's not working, but woo 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 woo. You have waves, right? And then particles, you know, you have, most of you have seen, like in some science class, you've seen electrons. You know, you have these little, you know, dot, 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 dot. You have these little electrons. Okay, we have these two different things. Totally different, separate, not the same thing. Now, lots of scientists came, started studying, said, you know what, started to say, wait a minute, now with these whole electromagnetic wave things, it gets a little complicated. So, in the video you just saw, basically, to kind of sum it up, in 1887, Heinrich Hertz discovered that shining a light on a material basically showed that electrons are ejected and that it depended on the frequency and not the amplitude. Long story short, and again, if you get into higher level chemistries, they explain this a lot more in detail. We're in ICP. We don't need to, you know, get into this in great detail. With a lot more explanation, a lot more equations, a lot more ringamoran. Basically, Einstein took Hertz's information and said that these electromagnetic waves behave as both a particle and as a wave, and this particle is called a photon. And this photon depends on the frequency at which the wave is at. So that's basically what you guys need to know, is that we have these things called photons, these particles, that depends on what energy the wave is at. So photons are a packet of energy. Okay, so photons are a packet of energy. The shorter the wavelength, the more energy a photon has. So, an electron can absorb photons. I don't know why I have that extra there. They can emit and absorb photons, and they can form the electromagnetic spectrum. So basically, an electron can take in this particular amount of energy, and when it does, it produces a certain something off of this particular spectrum. So, this is the spectrum. The electromagnetic spectrum is named for the range of electromagnetic waves when placed in order of increasing frequency. So if you notice, we get everything from radio waves to microwaves, infrared waves, visible light, ultraviolet rays, X-rays, gamma rays. Notice that the wavelength of radio waves gets shorter as you go along. So radio waves are the longest, gamma rays are the shortest. And that makes sense because the shorter the wavelength, the more energy it has. So gamma rays, lots of energy, very dangerous. And here's here's another example of your electromagnetic spectrum showing, I don't know what's going on here, showing another example of everything. There we go. Radio waves. They have the longest wavelengths with the shortest frequencies of all the electromagnetic waves. Okay, so we're used to radio waves. You know, you turn on your dial, listen to the radio, that kind of thing. Alright, so like the global positioning systems or GPS, they use radio waves in order to basically function. They measure the time it takes a radio wave to travel several satellites to receive, like go from receiver to receiver, and determine the distance to each satellite. So that's an example of using radio waves. And so we talked about a radio basically picks up radio waves through an antenna and converts it to sound waves. So each basically radio station broadcasts through a different frequency, and so that number on your radio dial basically tells you the frequency at which it functions at. Okay, an MRI, believe it or not, when you go to have a medical test called an MRI, called a magnetic resonance imaging, it uses short radio waves basically to create an image of whatever you're being tested. Microwaves are the next one over. Basically, they transfer energy to the water in the food, causing them to vibrate, and which transfers the energy to form heat within the food itself. So, microwaves are another example of electromagnetic radiation. Then the next one over is infrared rays. Infrared means below red. That's where we get the term infrared. It's shorter wavelength and higher frequency than the microwaves. So there's your next one over from a microwave itself. Just some uses for the actual infrared rays. You can feel the longest ones. You can feel the longest ones as the warmth on your skin. Warm objects give off more heat energy than cool objects. So, you know, we've probably all seen where you can use them as, like, you know, thermal imaging. I can't talk today. So, like, for example, you can have some special devices that can look at your house, and, you know, if it's hot, it shows up as different colors. That's, you know, obviously one of the uses. And that's called a thermogram, a picture that shows regions of different temperatures in the body. If you use it for your body, that's a thermogram. Temperatures are calculated by the amount of infrared radiation given off. Heat lamps give off infrared waves, and so people themselves, therefore, give off infrared waves. Okay, so there's all examples. Visible light. So this is probably the most common one to us in the sense that every day we use visible light. We see it, obviously, visible. Okay. We get all the colors that we are exposed to from visible light. It's a shorter wavelength and higher frequency than infrared rays. Electromagnetic waves that we can actually see. The longest wavelength is red light, and then the shortest wavelength is violet or purple light. So all the colors that we see are made from electromagnetic waves. The reason we see light is because it's diffracted. The bending of light waves around an object. As light passes around an object through an opening, it's diffracted or broken through basically the colors of a rainbow. We get the colors Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. So it's broken into those colors. Our eyes interpret color the same way. We're able to get all of those colors and interpret in that way. The next one over is ultraviolet rays. They're shorter wavelength and higher frequency than visible light. They carry more energy than visible light. One good use of ultraviolet light is actually used to kill bacteria. Sterilization of equipment. In fact, our goggles equipment is used. It has an ultraviolet bulb that we use to kill bacteria. Some hospitals are going to ultraviolet sterilization. They have little robots that they pull in and do a flash sterilization that sometimes it takes anywhere from a half hour to 2 hours that they put in a little room. There's various ways to use UV that actually kills bacteria. Of course, we know that if you get too much UV, it can cause skin cancer. And of course that we want to use skin block sunscreen to kill UV rays. And there's some fun examples of some skin cancer. Every time. UV does cause your skin to produce vitamin D, which is good for your teeth and bones. So some exposure to the sun is good. Obviously too much, though, is bad. X-rays. They're shorter wavelength and higher frequency than UV rays. They carry a great amount of energy, and they can penetrate most matter. Bones and teeth absorb X-rays. The light part of an X-ray image indicates a place where the X-ray was absorbed. Too much exposure, of course, to X-rays can cause cancer. A lead vest at the dentist protects organs from exposure. Gosh, stupid thing. I know, like, for example, my husband works in surgery, and when they do a lot of orthopedic surgeries where they have to take X-rays, he wears lead vests. They also have these little things on their badges that show when they've been exposed to too much X-rays, and then they tell them, hey, you can't be in any more X-rays, surgeries with X-rays, and so they try to do a lot of precautions to make sure that, hey, you don't get exposed too much. Gamma rays, shorter wavelength, higher frequency than X-rays, carries the greatest amount of energy, and then penetrates the most. Gamma rays, of course, are super dangerous. You want to make sure that you're not exposed to that if you can. This is evolved down in the nuclear level. We do use gamma rays for radiation treatments to help with cancer treatments. It's very harmful, of course, if not used correctly, because obviously it can kill our cells. So I put that as kind of a joke. The Incredible Hulk was, a victim of gamma radiation. But, if you explode a nuclear weapon, that's what it emits. It emits gamma radiation.